Hello students, we continue our study of problems in the class NP and more precisely in the class NP-complete, exploring this time problems that have a graph nature. The input it will be typically a graph, maybe some other variable, and we want to decide whether or not these problems, which are sometimes very classical and easy to present, are actually NP hard. That combined with these problems being in the class NP will give us that these problems are in the class NP-complete. If you watched Professor Svigoda's video, you saw that the following problems are in the class NP-complete. Independent set, which is checking for an independent set of a given size. The click, which is kind of an inverse problem of the independent set. Also, the source version is in the class NP-complete. And the vertex cover, which is a problem asking to find a set of vertices that touches every edge in a given graph of size at least certain certain number. All these problems has a optimization version which are not in the class NP, but they are still NP hard. I wanted to make this video to talk about one final problem that is referred to in the book as Rudrata path or Rudrata cycles. I will explore that problem in this video, and I wanted to give you an outline of a proof of NP completeness for the problem. I wanted to do it for two reasons essentially. One, to show you a classical problem that may seem not so difficult a priori, but it's actually NP hard, and it's actually quite popular. And also because I wanted to give you the word of the day, and I cannot do that on Professor Svigoda's video, so I want to do it now, and then we want to talk about Rudrata cycle. The word of the day is leones, and this picture shows you how kids in Cuba are fearless, and they actually tame lions for fun. So now that you know that you should not mess with Cuban kids, let's talk about our problem, Rudrata's path. What is the definition? The input is, again, a graph. It could be undirected or directed, doesn't really matter. And in this particular version, we are also given two vertices S and T. The goal is to find a path that starts at vertex S and ends at vertex T, with the extra property that every vertex in our graph is visited exactly once. Now, you may ask for a path that starts at vertex S and ends at the same vertex, thus making this path a cycle, and in such a case we call this the Rudrata cycle. Of course, the only vertex you visit twice is the very first vertex, or you can say that simply you visit everybody once in this cycle. So there are two problems here. Rudrata's path, which asks you for a path connecting two different vertices and visiting every vertex in the graph exactly once, or Rudrata's cycle, which asks you for a cycle that visits every vertex exactly once. In other words, you enter the vertex and you exit the vertex, and that's it. If you're thinking that this sounds very much like Hamiltonian cycles, well, you're right. This is actually the same problem, the same question. It was popularized as Hamiltonian cycle after the contributions by the Irish mathematician William Rowan Hamilton in the 19th century, but recently, trying to make history to Rudrata's mentioning of these problems in the 9th century, it's being called in certain textbooks as Rudrata's path and Rudrata's cycle. Other mathematicians and other scientists in history has mentioned this in different scenarios, and as Rudrata, let me just point this out, of course, Rudrata wasn't talking about a graph and cycles on a graph. He was talking about what it will be a Hamiltonian cycle or a Rudrata cycle on a chessboard by a knight. In the same way, it was mentioned like this by other scientists in the past. And Leonard Euler has a famous example in which he was presented with the problem of traversing a city which has certain number of bridges, and that was the only way to go from one part of town to another. I'm sorry about that, but it comes down to either Hamiltonian cycles or Rudrata cycles these days. This is the problem we want to talk about today, and I'm gonna show you again an outline of why this is an NP hard problem. One fair point to make here is that it's not much distinction between the problem of finding a path to the problem of finding a cycle, and let me show you quickly why is this the case. Imagine that you're given as an input Rudrata's ST path, and you want to check whether or not there exists a cycle, or to be more precise, you want to reduce the Rudrata ST path problem to the Rudrata cycle problem, well, here is a simple reduction. You take the input graph and you add a new vertex, a new artificial vertex V, together with two edges, one going from V to S and another one going from V to T. Now, if there is a path from S to T traversing every single vertex, you can complete the cycle by traversing from T to V and from V to S. And this, of course, will visit every vertex in your new graph. So there is a graph. If the initial graph has a Rudrata path, the final graph will have a Rudrata cycle. And of course, vice versa. If there is a cycle, the only way to go to vertex V will be through these two blue edges, and then you can remove those and you will get a path from S to T that visits every single vertex. So these two problems are quite similar, and actually if you prove or if you solve one of them in polynomial time, you will solve the other because both are NP-hard. We're going to show today a reduction to for the problem, the Rudrata cycles problem, from the vertex cover that you study with Professor Bigoda's video. Now we're going to do this reduction to finding a Rudrata cycle on a directed graph. There is not much of a difference for this class. You can assume that both the undirected case and the directed case are NP-hard if you want to use it in future assignments, but I will only present you this problem or this reduction for two reasons. One, because it's always nice to see these reductions and how they work, and most importantly perhaps because it's a very involved reduction. It may feel way more harder to come up with compared to the ones you have seen before. And I want to show you this idea for you to appreciate how complicated it could be to prove that a problem is actually hard. So sometimes it's as difficult to prove that a problem is hard to actually find a good algorithm or a good design to get a solution. Now, as the title says on this slide, we're proving that the Rudrata cycle actually is NP-hard, and we will not check whether or not this problem is in the class NP, although it's quite simple for you to check that at this point, so I hope you can do that. We're going to jump right into the reduction. Given an input of vertex cover, that will be a graph G and a natural number K. I want to build a directed graph H out of this graph, and I will like to use this number K somehow. And I will check whether, or I will outline for you why having a vertex cover on the first graph implies that we have a cycle visiting every vertex exactly once on the second, and vice versa. Now we will do this construction in three steps. The very first one is something we will call a gadget. What is this? This is going to be associated to every edge on the original graph G. So given an edge with vertex UV, we're going to build four vertices. We're going to label those vertices as UV in and UV out, and also VU in and VU out. So we're reversing the order of the vertices. And we're going to build six edges, which are these six red edges in the picture. Notice that this is a directed graph, so there are directions on these edges. That's why we have this loop connecting two vertices in the middle. I also are showing you some black edges that I will soon tell you where are they coming from. But the gadget, which is the first step, is to build out of every edge four vertices and six edges in our new graph. Of course, this step is polynomial on the input side. The second step is to build what we will call a chain of vertices. What is this? Well, given a vertex, let's call that vertex U, you have the neighbors. This is the number of edges out of U in the original graph G. That means that you will be involved in the construction of the many gadgets. This is the picture here showing you three gadgets. Well, we're going to connect those gadgets with edges going from the UVI out vertex of one to the UVI plus one in vertex of the other, which corresponds to those black edges I showed you before and those two edges I am showing you here. So we are connecting this sequence, if you want, of gadgets associated to the same vertex U through these edges that are black, and then we call that a change of the change of vertex associated to U. The last step is to add K new vertex, K artificial vertex. This K is the K given in the input of vertex cover. And then we want to have a number of edges associated to these vertices. We want to have outgoing edges from each of these vertices to each of the initial vertices of the change for each vertex u of the graph. And we're also going to have edges coming into xi from every last vertex of the change. Notice the picture, we have a chain from before, we have an initial vertex in that chain here, and we have an edge going from certain xi into that initial vertex, and then we have another edge in blue also going out of the final vertex of the chain into vertex xi. This happens for every vertex in the graph, every vertex u, and every vertex xi that we built. That is the 3 steps, and in my next slide I'm going to show you a full picture of how this transformation looks like for a simple graph G given. Here is the construction in full. The graph to our left is the given graph G, the input of vertex cover. K is equal to 2 for this input. You can immediately see there is a vertex cover of size 2 given by vertices x and u. But I am showing you on the right how the construction of the input for the Rudrata cycle problem will look like for this tiny little graph. Let me break it down in pieces for you. Every vertex u, v, x, and w will have a corresponding change, and we have shadows of different colors for each of the change. The 2 vertices in red outside corresponds to the vertices x1 and x2 that we built in step 3. As you can see, there is an edge going out of each of those vertices into the beginning of each change. Finally, there are also edges coming into this vertex xi from the end of each change. And the edges in blue are the gadgets. Every time you see across a blue edges or 2 blue edges crossing like this, that corresponds to an edge in the graph. As you can see, the edge uv will yield this gadget here, the edge vx will yield the gadget here, etc, etc. You get 5 gadgets, 1 per edge in your graph. Let's talk about why it is true that given a vertex cover there is a cycle in this graph to the right. My advice is for you to focus not too much on the details on how to build the cycle, and more on the cycle itself. Here I outlined how to build such a cycle. The idea is you have a vertex cover, you have k vertices at most, C1 up to Ck, which builds a cover, and you want to build a cycle. And how you want to do that? Well, you're going to start at x1, these artificial vertices that we created. You're going to go into C1 and you're going to traverse the change corresponding to C1. Then you're going to go to x2 from the last vertex of the change C1, and then you're going to move to C2 from x2. You're going to traverse the change associated to C2 and go on. You're going to move from one to another, alternating between xi and the change associated to ci. In the corresponding change, you will traverse the gadget following these rules, one of these rules, depending of whether you have a second vertex on the cover or not. This is outlined here. I am pretty sure you can follow that, but let me show you the cycle in the example just to give you a visualization of how the cycle will look like. Let me start at this vertex that I'm going to label x1, and let's say that u is the first vertex in my cover. We have 2 vertices here which form the cover, u and x. So let's call u the first one, why not? So we move into u, and then we check whether the second vertex in my in vertex belongs to the cover or not. So I enter here, the second vertex is w in this gadget, w is not in the cover, so I'm going to traverse the gadget going through the blue edges. Then I move to the next gadget. Now my vertex in the gadget is in the cover, so I will not use the blue edges, I will continue straight out of the gadget. In this new gadget, v is not in the cover, so I move through the blue edges. And then I am at the end of the change corresponding to u, so I move to x2. From x2 I enter the other vertex in the cover and I do the same. Is my vertex in the gadget, the other vertex in the gadget is on the cover? No, it's not. So I move through the blue edges. Then I move through to the next gadget. I check this gadget is built from another vertex in the cover. So I will go straight and I will not use the blue edges to the next gadget and so on, I complete my cycle. Notice that if you follow that cycle, you will visit every vertex in this graph exactly once. That proof that, or that show you how to build from a solution of vertex cover a solution of the Rudrata cycle problem in the new graph. Now we have to go the other way around. Given a solution of the Rudrata cycle, I need to find a vertex cover. Well, it can be shown that given such a cycle, there are exactly k chains that are traversed in that cycle. In other words, you don't traverse this change right here. We never traversed that change. We never traversed this change right here. We never visited these edges. So you only visit exactly k chains. This can be shown, and those vertices form a cover of the original graph G. I will not get into details of this proof because it is rather more technical. It requires a couple of induction steps, and it's not really the goal of this class. But I wanted to show you this proof because I found it pretty nice and pretty neat, and also a little bit more involved than the ones you will see in this class. Now, you are not required to remember this huge reduction moving forward. I will never ask you in the exam or in the assignments in the homeworks to do a reduction of these magnitudes. But I do want you to remember the Rudrata's path and Rudrata's cycle are both NP-complete. And I hope we can use those problems in our lecture when we meet on Tuesday. Maybe you will use it in the homework or in the exam. Until then, I see you all. I wanted to keep this video short because you also have another video to watch before this one. So I will see you guys on Tuesday to talk more about NP-complete. See you then.